These could be pieces of modern art. In fact, they are the microstructures developed by just a few of the different types of stainless steels available to solve corrosion problems. There are over 100 types to choose from, and as you may expect, they are all related to each other. It's like grafting different branches onto a tree. The trunk is carbon steel, and its closest relations are low-carbon ferritic steels containing chromium. These are relatively soft, but increasing their carbon content converts them into hard and strong martensitic steels. Steels in this branch contain both chromium and nickel. The nickel produces an austenitic structure which makes the steel tough and ductile. Adding more alloy elements to this austenitic structure produces special steels for very aggressive environments. There are also special ferritic steels. For instance, low-carbon, high-chromium steels containing molybdenum and niobium or titanium combine excellent corrosion properties with reasonable toughness and weldability. As the name implies, duplex steels contain both austenite and ferrite, giving them a combination of good corrosion resistance and good tensile properties. There are many other specialist stainless steels for specific applications, but they all have a place in the stainless steel family tree. With over 100 different stainless steel specifications to choose from, there's a solution to almost any corrosion problem. However, almost 70% of all stainless steels used come from the austenitic group. Their combination of good corrosion resistance and high ductility make them an obvious choice for industrial equipment, as well as for sinks, tableware, and many everyday items. The same sort of 18% chromium, 10% nickel stainless steel is also widely used in buildings, combining permanent good looks with easy fabrication and low ownership costs. It's possible to increase the strength of this steel by cold working it, and this stronger version is used to design lighter, longer-lasting things, such as this high-speed train. The response to cold working can be increased by altering the chromium and nickel content, and this type of higher steel strength was used for Eurotunnel vehicle wagons to obtain a more cost-effective, lighter design. Alternatively, the composition can be adjusted to reduce the cold working response, allowing components to be made easier and cheaper. For instance, this piece of steel can be made into a pen body like this by one continuous sequence of pressings, because it remains ductile and soft enough at each stage to accommodate further deformation. Although chromium-nickel stainless steels have good resistance to general corrosion, they are susceptible to pitting by salt water, chlorides and similar elements. However, adding molybdenum greatly increases the steel's resistance to pitting corrosion. So, stainless steels containing molybdenum are specified for this environment. Adding more molybdenum and some nitrogen further increases the steel's resistance to pitting corrosion, making it suitable for the very aggressive environments encountered in paper pulp production. Here, logs from renewable managed forests are being used. The wood fibers are broken down by both mechanical and chemical methods to produce these continuous sheets of pulp. Although austenitic steels are easy to weld, under some conditions chromium carbide forms at grain boundaries in the heat-affected zone. But the migration of chromium atoms to form the carbide leaves insufficient chromium to form a passive film, and corrosion can occur in these regions. One solution is to use steels containing either titanium or niobium. They form stable carbides, and so reduce the amount of carbon available to form chromium carbide. These stabilized steels are still used for heavy sections, but modern steelmaking methods make them unnecessary for thinner material. It's now possible to make steels with such a low carbon content that there simply isn't enough time for chromium carbide to form in the heat-affected zone. Of course, there are times when chromium carbide formation can be a good thing, and it is often used to increase the hot strength of heat-resisting stainless steel castings, such as these in a furnace floor. Before leaving austenitic steels, it is useful to remember that free machining grades have been developed to reduce manufacturing costs, but their corrosion resistance may be slightly reduced. Ferritic steels account for roughly 30% of all stainless steels used. The simplest ones contain 10.5% chromium, the minimum needed to develop a passive film. The weldable grades are excellent alternatives to the galvanized mild steel formerly used in these mineral wagons. They have also been used to solve corrosion problems with the structural framework of buses. However, 17% chromium steel is the most widely used ferritic type. It may not have the corrosion resistance, formability or weldability of austenitic steels, but it is ideal for many applications. Adding a little molybdenum to resist pitting corrosion makes this steel a popular choice for vehicle trim. The martensitic high-carbon 12% chromium steels combine corrosion resistance with the hardness needed to produce a sharp cutting edge, something that the ductile austenitic steel used for the protective apron and glove could never do. Add molybdenum, nickel and a few other alloys to a martensitic steel and you have an excellent material for steam turbine blades and other engineering applications. The good corrosion resistance of duplex steel has already been mentioned, but the high mechanical properties of modern duplex steels makes them ideal for high-integrity structural applications such as this exterior structure. It's also been chosen to reinforce the concrete in this bridge. And cast duplex stainless steel was specified for these turbine wheels, which will spend all their working life surrounded by water. So there you have it. There's not just one stainless steel, but a whole family of steels, each one with a different combination of mechanical properties and corrosion resistance to meet the demands of today's world and tomorrow's.